Okay, there you go. So you can see we use the z-score formula. So you take your data value, subtract the mean from it, and divide that subtraction by the standard deviation. So what this basically does is it uses the mean as 0 and your standard deviation of 1, and we do that standardization so that we can actually use the table. So remember how we talked about we can use tables, or we can obviously use technology to find the area under the curve. And then we also talked about how the area under the curve can represent proportion, or it can represent a probability, which would be a percentage value. So last time we talked about how to find the area to the left of your desired random variable x, or whatever your value of x would be. We talked about how to find the area to the left. We talked about how to find the area to the right of the random value or random variable x, and then we also talked about the in between. And you can kind of see there's this nice little table here, which kind of shows you how you use the table 5 in your appendix A to find these areas. So we did the examples which were more in like a generic sense than actually using applications as our examples. And let me just show you where you can find that table 5. So it's part of your textbook, but also, as I had mentioned last time, there is this formulas and tables from textbook link in your MyLab statistics, which is the second option in your D2L course shell. So if you go to that, and you can download this, I saved this as a PDF if you wanted to download it. I guess whenever he decides to come up. Okay, till he is decided to come up, let me show you. So go under your menu option, table of contents in your textbook, scroll down till you get to appendix A. And I think it's pages 11. Yeah, so you can see on page 11 of the appendix is the negative side of the normal distribution table, because your z-scores can be negative if your random variable is a number smaller than the mean, and your z-scores can be positive if your random variable was a number larger than the mean, right? So you can see these are the two tables we would be using for table 5. And there we go. So you can see how I have broken this down. And Cameron, to answer your question, this also may be something you can use for some of the concepts also, because it does have all the definitions and stuff. In here, obviously, mainly I focused on every formula that we had used, though remember for most of these, I showed you how to use the built-in function, so you guys didn't have to do like the long-handed calculation. So you can see, so this is the empirical rule we're talking about, right? We're revisiting all of these here in chapter 7 again. But I'm gonna scroll through here quickly so I can show you as you get towards the end, you will start seeing these tables. So you'll see we're starting with table 1. These are your binomial probability ones that we saw in chapter 6. And then again, we should be able to see the table 5. So you can download this. You can print pages if you are like, I know this is something I'm going to be using often. You can download them as well. So again, that's in this handout called Formulas and Tables from textbook. And then of course, it's also part of your textbook page itself. So let's continue on with section 7.2. So basically we're talking about, okay, so how do we find the value of a random, normal random variable? So remember, this is where we are now applying this to some sort of a application problem, and not just talking in terms of a generic, if your z value is this, what's the area going to be? So we're kind of taking what we learned last time and now applying it to real world examples per se. So you can see that they're saying often we do not want to find the proportion, probability, or percentile of a given value of a normal random variable normally, or rather, we want to find the value of a normal random variable that corresponds to a certain proportion, probability, or percentile. So basically we are saying you're given the proportion, you're given the percentile or the probability, and we want to know what value is associated with that percentile or with that probability. So here they're saying, okay, we might, I just get my pointer here. we might want to know the height of a 3-year-old girl who is at the 20th percentile. So we know the 20th percentile, but we don't know what height goes with that 20th percentile. Or we might want to know the scores on a standardized exam that separates the middle 90% of the scores from the top and bottom 5%. So again, we know the percentile or the percentage or the probability proportion, but we don't know what score or what value goes with it. So let's take a look at example 3 here. They're telling you the height of a pediatrician's 3-year-old females are approximately normally distributed. And again, remember, this term, approximately normally distributed, is very crucial to have in our example in the data that we're looking at, because otherwise we cannot apply these concepts of the normal curve or normal probability to the example. So here we're telling the heights have a mean of 38.72 inches, and there's a standard deviation of 3.17 inches. And basically the same question they presented above, what would be the height of a 3-year-old female who falls into that 20th percentile? So as you can see, kind of similar steps that we did last time. They're asking us to draw the normal curve and shade the area. Now we'll be working backwards. They're asking us to use the table find to table 5 to find the z-score. So remember in the examples we did on Monday, we were given the z-score and we were finding the percentile from the body of the table. But this time we are given the percentile and they're asking us to work backwards to find the z-score that would correspond with it. And then based on that, we obtain the normal value that's associated with that percentile. So you will see this little calculation on the bottom. Let me put that on a little bit. Because look at the formula they've given you here. It's given to you as x equals mu times z, mu plus z times sigma, which is the standard deviation. So you're taking the mean, and to that you're adding a product of the z-score with the standard deviation. So this is basically the same formula that we have here for finding the z-score that is being rewritten, right? So simple algebra here. We start by multiplying both sides by sigma. So basically what happens is if you're multiplying both sides by sigma, then these guys would cancel out, right? So you're just left with x minus mu on the right-hand side. You get z times sigma on the left. And then of course you get x by itself. We add the mu on both sides. Of course, that will cancel it on the left, on the right-hand side. So you're just left with x on one side. And then on the other side, you're left with mu plus z times sigma, which is what we have over here. So they're just showing you that as a footnote of how they came up with the formula for finding the x value. And again, if you know one, you can work backwards to find the other if you're comfortable doing that calculation. So it's up to you if you want to remember 2 different formulas or just use one. Alrighty, so now we know what the steps are. So let's find out what that 20th percentile height for a 3-year-old female will be. So you can see, again, in our normal curve, remember the entire thing is 100% or a total of 1. So if we're talking 20th percentile, we're saying 20% of the values will be below where your 20th percentile is. So you're shading 20% on the left-hand side, which means 80% or 0.8 is left on the right-hand side. So that shaded area is what we are interested in finding. So the way you do this is you look in your table and you see where 0.20, right? Because that's our 20th percentage will be. So you will see the positive table actually starts at 50%, right? Because the top half is 50%, bottom half is 50%, which means we need to go to the negative side of our table 5 to be able to find that percentage. So we will go back to that negative table. And you will see how this table and the way the numbers are written, this guy also ends at 50%, right? So that's how the two tables are. So now we need to go find where 0.20 will be, or the number closest to it. So I'm already seeing some 2 zeros here. So I know I'm in the right direction. I'm seeing 2005 and 1977. So not exactly 0.2000. So what that means is you have to see between these two numbers. I don't know if you guys can see that highlighted. It's very light. Okay, a little bit better. So you can kind of see the two numbers we are interested in is 0.2005 and 0.1977. Now, I would say think about 2000 and think which number is closer to 2000. Is 1977 closer to 2000 or is 2005 closer to 2000? 2005. So that's the value you are going to use to find your z-score. Not sure if we want to do that, but we're looking for 2005. So you will see on the left-hand side, it seems to correspond with negative 0.08. Right? So we've got negative 0. Not 0.8, just negative 0.8, and then on the top, it's going with 0.4 or 0.04. So that's going to become your second decimal. And you can of course count because the way the decimals are, this column is 0.00, 0.01, 2, 3, 4. So you can count that way also. So the z-score associated with the value closest to 28th percentile is going to be negative 0.84, and let's see what your textbook has to say. If you guys can see, let me erase this. There. So here you can see same value, 0.2005, which corresponds to the z-score of negative 0.84. And now we use that to plug into our formula over here. So they gave us the mu and the sigma, the mean and the standard deviation in the problem itself. We just calculated our z-score. So you can see we plug that into our formula, and we are saying approximately a 3-year-old female will have a height of 36.1 inches, so approximately 3 feet tall, right? To be in the 20th percentile, which means 20% of 3-year-old females at this pediatrician's office will be shorter than this person. So that's how you calculate your height when you're given the percentile. Okay. So, and on the right-hand side, you can again see they're using technology. And usually they use TI-84, but they could be using Minitab in there. And of course, I'll show you these examples with Google Sheets, since that's kind of our program that we use. So at least, are we kind of getting a sense of how we use the percentage to go backwards and calculate X value corresponding to it? Okay, let's do one more. So this one, you can see the scores earned on the mathematics proportion of the SAT, which is, of course, as we know, a college entrance exam, are again approximately normally distributed. We need that term that has a mean of 516 and a standard deviation of 116. What scores separate the middle 90% of test takers from the bottom and the top 5%? So again, so basically, since we're talking about the top and the bottom, we're talking about the 5th percentile, as you can see in the last sentence of that problem, and we're talking about the 95th percentile because you have to have 5% on the bottom, 5% on the top, and you can obviously see those would be these shaded areas here. So they basically want to know what those scores will be at the bottom 5% and the top 5%. So then we can say what the middle 90% of the scores would look like. So we know what we are looking for. in our example here. So let's go about taking a look at this. So obviously then we need to go for 0.05, which will be equivalent to the 5% of the bottom half, and then we will also need to use the 0.95, yeah, so the 0.95% to get the top 5%. So again, going back to our table, you will need to go to two different sides of the table here, because the bottom 5% will of course be option so 5%, right? 0.05. So 0.05, we should only have 1 0 after the decimal, so it's gotta be somewhere here. So again, and I'm not using the highlighter for that. You can see this is where we are straddling that 5%. Let me see. So 0.05 is what we're looking for, which is again going to be between these two values. So again, which one is closer? Again, think about 500 as the last three digits. So will 505 be closer, or will 495 be closer to the 500 that we're looking?
Same.
It's the same, because you are either 5 units below or 5 units above the 0.05 per se, you know, in the 10,000 category that we're looking at. So normally, what you do is you take the average of the two z-scores, which is the normal practice. And then what is your textbook? Yeah, you're taking the mean of the two z-scores. So as you will see, the two z-scores will come out to be, on the left-hand side, we have negative 1.6, and then of course we have 0.04 and 0.05. So your two z-scores are going to be okay, so on the left-hand side, I've got negative 1.64 at the top and negative 1.65 using these two numbers. So if you take an average of that, you will see it comes out to be negative between 40 and 50 will be 45. So it will go to 3 decimal places and it becomes negative 1.65. And I believe that's what we have. Yeah, you will see you had negative 1.65. Now, for the 95% calculation that we have to do, we will need to go to the positive side of the table now. So for 95%, all right, so 95%, 28, looks like it's gonna be this guy. So that's gonna be 94959505, and actually you are in the same boat. You are going to be 5 units away in either case. So if you think about 0.9500, right, that's 95% in 4 decimal places. You're looking for what number is closest to 9,500, right? If we just drop the decimal for now. So 9495 is 5 units away from becoming 9,500. And of course, 9505 is 5 units over of the 9,500. And you will actually notice in this case, we are getting the positive equivalent of the same z-score we got earlier. So again, when you take the average of 1.64, 1.65, they're just positive numbers here. You will get 1.645 as the average of these two z-scores. And that's the same answer. That's the same answer you will see your textbook has for the positive side. So now that we have both our z-scores, negative 1.645 and positive 1.645 from our table, plug that into that same formula again, and it will tell you the threshold for the 5th percentile and for the 95th percentile. So at the bottom, it's going to be at the 5th percentile. And then of course, at the top end for the 95th percentile, it's going to be 7 or 7. So you're looking at the middle 90% being sandwiched between 325 and 707 for your SAT scores for the college entrance. You can see the interpretation at the bottom here. So we're saying SAT math scores that separate the middle 90% from the top and bottom 5% are 325 and 707. Or you can also say it as a student who scores 325 on the SAT will be at the 5th percentile, so only 5% of the scores will be below theirs. And if a student scores at 707, then we would say 95% of the people who took the SAT will score below this person. And you will actually see questions which will ask you to find that middle 50%, middle 80%, you know, kind of like this. They are also talking about, and this might actually make your life easier if you think about symmetry, which is again the beauty of using a normal distribution. So we know that 5% and 95% are both at the tail, right? So imagine if we fold that normal curve, 9%, 95% and 5% fall at the same place. So that's also the reason why your z-scores came out to be positive and negatives of the same number. So if you calculate one and you know there's that symmetry, you don't really even have to calculate the other, just make it positive or negative depending on which side of the mean you are on. So that may be, like I said, saving you time if you can remember, hey, I've got symmetry. They're also talking about notation, which can kind of help you identify which number you are looking at. So you can see we use the notation of z sub alpha to represent the area for which you are looking at. So, you know, we can say, I'm trying to find the z-score for, you know, the 5th percentile. I'm trying to find the z-score for the 10th percentile. And you can kind of put that subtext there so you know which number you are looking at. This one is asking you to find the value of z sub 0.10, which is basically telling us to find the area under the curve, the standard normal curve, where you're looking for the right-hand side of the 10%. So if you have right-hand side 10%, then obviously that means 90% on the left-hand side, right? So you would go and find the 90th percentile and then find the z-score that would go with that. So I definitely ask you guys to play around with that a little bit to get some sense of just different calculations. As always, you've got your technology step-by-step here. And I showed you this last time, but let me show you again. So you can see the main function we will be using, and that's under the Excel, is the norm dot distribution. And when we're ready to talk about reverse calculations, which we've done now, we'll be using the norm dot inverse. So let's take a look at some examples here. We did some of these generic ones last time, but let's do some applications. At incubation times, we just talked about that in presentation. Alrighty, I will put this again in our classroom example Google Sheets file that we've been using. So let me copy this over. Okay. So as you can see, we're talking about the mean incubation time of fertilized chicken eggs kept at Okay, 105.5 degrees Fahrenheit. In a still air incubator is 21 days. So the mean time for incubation is 21 days. Suppose that the incubation times are approximately normally distributed. Again, the keyword we always want to make sure is there. Has a standard deviation of 1 day. And you can see this is from the University of Illinois Extension. So they're asking us to draw a normal model that describes egg incubation types of fertilized chicken eggs, find and interpret the probability that a randomly selected fertilized egg hatches in less than 20 days. Find and interpret the probability that a randomly selected fertilized egg takes more than or over 22 days to hatch. And then you can see the last one is between 19 and 21 days. Would it be unusual for an egg to hatch in less than 18 days? And then the So first, we do want to come and create your, you can go ahead and create your normal model as they're talking about. So as you can see, if we started out with, and I'm just gonna freehand it for now and show you how to use technology to do that. Normal curve, we know our mean is going to be right in the center. So they're telling us the mean incubation time for these fertilized chicken eggs is 21 days. They're telling us we have a standard deviation of 1 day. So, if we did the 68, 95, 99.7, you would be going, and again, guys, this is very rough sketch. So remember, it's 1 day. So you subtract 1 day and you add 1 day, right? So you go from 20 to 22 for the 68%. Then for the 95%, we go 2 standard deviations out. So we subtract 1 more from 20, we add 1 more to 22, so that puts us at 23, and then our 99.7 is where again we subtract 1 more, so that goes down to 18, and then add 1 more, which goes up to 24. So, and again, we put those percentages in. This one here, we are looking at 68%. 2 standard deviations out, we are looking at 95%, and then of course, 3 standard deviations out, we're looking at 99.7%. So here you can see we are actually given the same values as what we are seeing in our 1, 2, 3 standard deviations away from the mean. So the first one is asking for fertilized chicken egg that hatches in less than 20 days. So you can see less than 20 days is going to be from here all the way to the end, right? So it's going to be this little section over here. So can you tell me what that probability is going to be for less than 20 days? And remember, this is 1 standard deviation away from the mean. This is 2 standard deviations away, 3 standard deviations away, and this is of course on the positive. So what is the probability going to be on the left-hand side from 20 days? In less than 20 days, fertilized chicken egg is hatching. Think about that 20 is at 1 standard deviation below the mean. So we know this starts at 68%, right? That's 1 standard deviation above and below. So try to use symmetry, and you guys have done this kind of math in chapter 3, so this is not new for you. How do we calculate that probability for the left-hand side of 20% or 20 days? What do we think? I should know the answer to this. Again, right here is the cutoff for 20 days. They are telling us what's the probability that a fertilized chicken egg will hatch in less than 20 days. So if from here all the way to 22 days makes 68% total of your data set, well, half of that is going to be 34%. So we know something. So we know this section just from the mean to where that 20 days is. This will be 34% because that's half of 68. We know the left half from the mean is 50%. So we know from here all the way till the tail is half, which is 50%. So you'll do 34 subtracted from 50, which will end up giving you 16%. Now, there are many different ways you can do the math because, calculations can work in different ways, but I think that's going to be the easiest way of looking at it. So you do 50% minus 34%, which will give you 16%. So we will say that, six if they want a decimal answer. Of course, you can say 16% if they want a percentage. But yeah, the probability is going to be 16% or 0.16. Now they're asking us, what is the probability that it will take the randomly selected egg over 22 days to hatch? So think about those 22 days, where it's at, and what will that percentage come out to? So it will take over 22 days to hatch. So of course, as you can see, and I'm just going to go back to using green here for now. This is 22 days here, and let's say more than 22 days or over 22 days, which will of course be all the way to the tail. We're looking at this section. So what will that probability come out to be? Okay. What are we seeing in that image? Do we see symmetry between the shaded part on the left green, the left green shaded something? I'm mincing my words here, and the right. They are the same, right? Because they are both one standard deviation marker, either below or above the mean. So that area is actually going to be the same. And you can do the math again if you want, and it's still going to come out to be the same math, because you will see between the mean and that 22, that's one standard deviation above the mean, which tells you this little section also is going to be half of 68, which is 34%. And again, the right half is going to be 50%. So we know the right half from the mean till the end is 50%. So same math, 34 subtracted from 50 will give you 16. So even more than 22 days is going to be the same calculation. Okay, so those two were fairly easy. Now let's see what part B will give us. So this one is saying between 19 and 21 days. So they're not giving you entire 2 standard deviations below and 2 standard deviations above. Sorry, it's going to be a lot of writing on top of each other, but we're going from 19, which is this side here, So that was 2 standard deviations below the mean. In 21 days, and remember the 21 days was the center where the mean is. So it's this dark brown border that I'm drawing. Or dark maroon, whatever. Between 19 and 21 days. So you can see that's 2 standard deviations below the mean and the mean itself. So how much of this area are we talking about here? So that's going to be this section here and this section. Do we have an idea? 47.5, and you want to tell me how you got there? Perfect, and that's exactly what you need to do. Very nice. So yeah, because we know 2 standard deviations below and 2 standard deviations above is a total of 95%. So divide that by half and you've got your 47.5. Perfect. So yeah, that. Yeah, take 95% divided by 2 and you get 7.5%, which again, the probability and again, as a decimal, that will be 0.47. All right, perfect. Now, the question is, would it be unusual for an egg to hatch in less than 18 days? So when we're talking about less than 18 days, we're talking to the left-hand side of the 3 standard deviations below the mean. We're talking about this little tail over here, which is less than 18 days. So think about it again, 3 standard deviations below and 3 standard deviations above is a total of 99.7%. So how much area are we talking about here on this left-hand side tail? If we have 99.7 between 3 standard deviations above and below, what do you think those 2 tails will be? And then what will 1/2 of that? Perfect, yes. So again, let me show you that math. So we are talking 3 standard deviations above and below is 99.7. So of course, subtract that from 1. We should have tracked that. So we're doing 1, or you can do hundreds, since I'm using percentages right now. You can do 100 minus 99 for 7, which leaves you with 0.3. So 0.3 is going to be the total of the 2 tails. So you have to then divide this by half, and you can see that gives you 0.15. So yeah, in terms of percentages, this will be 0.15. And remember, this is in percent, which means as a decimal, this number is going to be even smaller, because as a decimal, what will this be when I convert this into a decimal? This 0.15%. Yeah, you insert 2 extra zeros after the decimal. So based on that probability, would we say, is it unusual for an egg to hatch in less than 13 days? Yes, it is, because that number is closer to 0 than anything else. So yeah, we would say it is unusual, because the percentage is, or the probability is very, very low that this thing will happen. Right. Savings, right. And then for part E. Did any of you have any questions on this exam? How to break down the math? All good? I will try to see if there is a way for me to take my scratchings here and insert that as an image into. I'm trying to save it as a PDF, but it's doing the whole screen, so I might have to do a little editing, but at least I'm saving it for now. So I don't have to like go back and draw it. Alrighty, so this was obviously a pretty straightforward one because we didn't have to use the table 5 to come up with any of our probabilities or anything of that sort. So let's see if I can find something that does actually help us with. Yeah, we can work with this one. Let's do. Seven. So let's look. I guess we went from should and next to humans. So again, just to do a rough sketch so that we have something to kind of follow along. You can see in this example, we're saying the lengths of human pregnancies are again approximately normally distributed with a mean of 266 days and a standard deviation of 16 days. So just using that information, let's see what that normal curve would look like. So again, mean is going to be right in the center at 266 days. So that's the quick math I was doing, because if you add 266 with 16, of course, that's going to be a number much larger than 270, since 270 is only 4 days away from 266. 240, of course, as you can see, is also not going to fall into that 16. So this is where we know that we're not using just a simple empirical rule. We will have to use the table to do some math for us. So I'll show you with the table, but then I'll also show you with the built-in functions. So let's go ahead and look at part A. So they're saying what proportion of pregnancies last more than 270 days? So as I said, 270 days is only 4 days away from 266. And if you look at 266 plus 16, and I'm just going to do some scratch work here. So if we said, okay, if I take 266 and I add 16 to it, which would take me to 1 standard deviation above the mean, you can see that takes us to 82. So we're not quite that far away from the mean when we're talking about 270 days. So I'm actually going to mark it pretty close to that 266. And then, of course, I'm not on scale, so this is very rough sketch here. So this will be our 270 marker. And they're saying, what's the proportion that the pregnancies last more than, right? So if we're talking more than, then of course, we're going all the way till the tail end of our normal distribution curve over here. And this is the percentage that we're trying to find. Now you will see in this example, they didn't give us the probability or the percentile. They actually gave us the X value, and we need to go backwards and find the probability for that using the table. So that's what you're going to do in part A, is first find your Z-score. So Z-score for Z-score for X equal to, what is it, 270? Okay, so let's do that. So remember, the formula is you take your X value. So our X is 270, our mean is 266, our standard deviation is 16. So using that, since you have to do the subtraction first, we're gonna put it in parentheses, so it's 270x minus the mean of 266, and then you divide that subtraction by the standard deviation of 16. So you will see how I put that subtraction in parentheses, because we need to tell the calculator, do the subtraction first, then when you have the answer, do the division. So z-score of 0.25. So 270 is a number larger than the mean, so you are going to get a positive z-score. So now, again, 0.25, so 0.2 0.2 is going to be right over here. And you can see 0.05 is right here, so you want to see where they will intersect with each other. And you can see it's intersecting at 5987. Since you were not here last time, just to remind you, the table always gives you the area on the left-hand side of the z-score. So whenever you are being asked to find more than, remember, we need to do the complement rule. So 59, and I'm just gonna write that 5987 here, and then let's go back to our. Okay. There we go. So this was the z-score. Now, how do we do the math for this? So remember, to find your probability, we will be doing 1 minus the answer we got. So 0.5987 subtracted from 1. And that's telling you the probability for the right-hand side is going to be 40.13, which of course then as a percentage will be 40.13%. So I want to take this number, let's convert it to a percentage, and you can use these little formatting options at the top, and you can see just clicking on that changes the decimal to a percent. So approximately, if we were to randomly select a human pregnancy, it would take, we would say about 40% of those would be longer than 270 days. And, of course, that's always a possibility because these are such subjective cases that every person's time period can come out to be slightly different. Okay, so question on calculating this probability. Okay, so far, alrighty. Now, let me show you how do we do this with a built-in function. So remember, the built-in function is norm dot distribution. Norm dot distribution, there we go. So equal to norm dot dist. And then your x value first, which was 270. Your mean, which is 266. Standard deviation was 16. And I don't think this is gonna be- What type of false? I think it should be false and not true, but let's see what that is. Okay, so it is gonna be. So as you will see, this is the same value as that 59, and I'm like, kind of. From the table, we got 0.5987, which is what we then subtracted from here. And that's the same thing you will need to do in this case. So you can use the norm dot distribution to find your probability, and you will see in that case, we don't have to use the table then, right? Because the formula is doing the table work for us. And then you do the same thing over here. You will do 1 minus this probability value that you just came up with, and then convert it into a decimal, I'm sorry, into a percentage. Questions on part A? For part B, they are asking us for less than 250 days. So if we take 266 and subtract 16 from it, so that's 1 standard deviation below, you will see that's where we land at 250, right? So this is a known value for us. So if we did less than 250, so that should be 1 standard deviation away from the mean. So 250, and that is 1 standard deviation below. So again, we already did this question with the chicken incubation time. What will be this percentage here? It's gonna be same thing, 16%. Because remember, between the 250 and the mean is 34%. So you're doing the same thing, right? 50 minus 34. But just to again show you with the built-in function, let's do norm dot distribution, so equal to norm dot dist, and our x value, actually, I need to change that, sorry. Mean, standard deviation, and then mean. So let me just change that 270 to 250. And since this was less than, obviously we do not need to do any math here, because that will automatically be the answer. So you are going to get a more approximate or a more precise answer than we would be by table. So this, or 16% if you did it back. Okay. All right, that was part B. Part C is asking us for the proportion that is between 240 and 280. So 240 will be obviously a little bit lower than 250. And what was the other one? 280, which would of course be 10 units larger than 270. That's 280. So this is the area you are looking at. So if you will remember, whether you use the table or the built-in function, when we use the x value of 240, it's going to give you the area to the left of 240. When you use the x value of 280, it's going to give you the area to the left of 280. So what's going to happen is, okay, I'm going to use black this time, but I'll probably need to erase it. So basically think about this. When we do the area to the left of 240, it's going to give us this region, right? When we do the area to the left of 280, okay, so to the left of 280, which would be here, would give you all of this. So you will see how that black overlaps with the purple. So what you're actually going to do is find the two probabilities, and then you have to subtract them to find the in-between value. So that's what we're going to be doing over here. So let's take a look at these two. So this was part C. Okay, so this is between 240 and, so let's call it X1, which is 240. Let's call it X2, which is 280. And then of course our mean and standard deviation stays the same. So let's do the norm dot distribution for the first one. So norm dot dist for 240, comma, the mean, comma, the standard deviation, and then we want to do true. And we're gonna do the same thing for 280, so norm dot distribution for 280. Then the mean, then the standard deviation, and again, you are doing true. So look how different those percentages are. You've got about 5% for the 240, and you've got about 80% or 81% for the 280. So now when you do the difference between these two, it will give you that in-between area. So that probability, as you can see, comes out to be let's change that to a percentage. They're asking for proportion, so you technically don't need percentage. With proportions, you would just round it to 4 decimal places. So you can kind of see it's going to come out to be 7.7571 or just approximately 75.71%. So we're saying if you randomly select pregnancy, human pregnancy, about 75% of them will take between 240 and 280 days of length for the human pregnancy. So this guy was part C. Part D is asking us for more than 280. So as you can imagine, more than 280 is obviously on the right-hand side. So on the right-hand side of 280 is going to be this here in red. And here's the awesome thing. We've already done the norm dot distribution for 280. So you just have to do a little bit of calculation to find the right-hand side. Because for this guy, we already have the math for this because this is what we did here. Because remember, this was the guy with 280, 266, and 16. Now, as we know, these formulas are set up for the left-hand side. We want right-hand side. So what you will do is 1 minus this number, and that's going to give you the probability for more than 280. So you can see a very small percentage of pregnancies fall into longer than 280 days, approximately 19%. Okay, so now they're asking you, what is the probability, and this is part E, that a randomly selected pregnancy lasts no more than 245 days? How do we describe no more than? Yeah, because if you remember from trying to find that table where we did the binomial, because that's where they talk about those symbols that you have to use. And again, guys, that is something I would definitely recommend you to keep handy. Because we will actually be revisiting probabilities, binomial being used with normal here in the next section. Right. So this is what I'm talking about. These terminologies and what their math symbols represent will really, really come in handy as you're working through this. So what was our question? What is the probability that a randomly selected pregnancy lasts no more than 245 days? So you will see no more than is telling you that's the maximum, right? Kind of what you were talking about. So the only thing you need to remember is that we are also including that endpoint in our calculation. So in this case, we're basically saying at most 245 days, but nothing longer than that. So if we're talking about 245 days here, we're gonna try yellow, which you may not even get. But we know 245 is gonna be right there, halfway between 240 and 250, so this is 245, and then of course that means no more than, or everything less than that. So we're talking about this area for 245. So what do you think that guy comes out to? Does that seem like a legit answer? This was your number here for 240. You remember from part C. For 240, we got a percentage of 0.05. 245 is giving you a percentage of 0.09. Yeah, because they're not that far away from each other, right? So there should not be a huge difference in probabilities. So, so that probability is going to be about 100%. Okay, a very preterm baby is one whose gestation period is less than 224 days. Are very preterm babies unusual? And of course, we can see 224 will be really close to that tail, wouldn't it, on the left hand? Oh, sorry, 24. So let's see what 224 will look like. So we can, based on that, we can then say, is this going to be unusual or not? So let's go this. 224. Yeah, let's see, I'll be on distribution, and you will see at this point, I'm not even going back to the table anymore. I'm just using the built-in functions because they help me figure out my percentage without having to, go navigate through the table. So look at how small that decimal answer is. It's 0.004. So even when I convert it into a percentage, it's going to be a number smaller than 1%. I mean, not even a total of 0.5%, right? So based on that, what would you say are very preterm pregnancies unusual? Yes, they are, because that's a very small probability. So yes. Questions? So next time, I do actually have a project for you guys to work on this. So it will help you kind of get used to using the norm dot distribution function. I will also show you actually how we can graph this little normal curve in Google Sheets. So, I'm not doing like crazy hand sketching over here. So I'll show you that. And then next time, we also want to talk about how to use the norm dot inverse function. So that way, if you're given the percentage, how do we work backwards to find the z-score and therefore the x value? So we'll do that. Next time we're at 3:59, so it really doesn't make sense for me to start like a whole new example. Any questions on what we did today here? Doing okay? Yeah? Did you ever figure out if you needed help? Okay, let me know, okay. And you were doing okay on your chapter 6? Did everything work out okay? Yeah? Omar, I guess you're the only one left. Any questions? Alrighty, guys. So enjoy your Wednesday, enjoy your weekend, and I will see you on Monday. All right? Take care, everyone. Be careful.